most of the things we measure just have one measurement, right? Height, weight, distance. But things frequently have more than one component to their measurement. We talked about this a little bit when we were talking about parametric equations. Do you remember we talked about how if you just had a parabola and you had the equation for the parabola, all you would know is what the path was. So then we did parametric equations. We identified each point separately. Right? We identified the x-coordinate and the y-coordinate separately, based as a function of time. For example, if you were talking about a rocket ship that had launched, you might say that, at a certain point you would say the altitude is so many thousand feet and the rocket is downrange so many miles. So it would be altitude and then downrange. So you'd be measuring it in two different ways. Vectors have two attributes. One is their direction, and the other is their magnitude. This would be a vector. This would be a vector that's, let's say we were, let's say we were traveling. This would be a vector that showed that we were traveling due east, right, because it's pointed just straight to the right, and it might show maybe 12 miles. Let me give you an example of what we're talking about. Let's pretend we're in a boat, we're traveling due north, and we're traveling at 12 miles an hour. After an hour, how far would we get? 12 miles. This is what would represent that. Okay? The due north is the direction. The length of the vector is the magnitude, and in this case it would represent the distance. Okay? But wait. What if we had a headwind of 5 miles per hour? How far would we get in 1 hour? 7 miles. How'd you figure that out? Right, you subtracted them. What you actually did, intuitively, was subtract the two vectors. You translate one of the vectors so that its tail lines up with the head of the other one. Okay? If instead of having a headwind, right, where we had to subtract the two, what if we had a tailwind of 5 miles an hour? How far would we get? 17. Why? Intuitively, what did you do? You added them. You set it up so that one, the tail of one was at the head of the other, and off it went. So, right, there's your translation. Right. Your new resultant vector is there, and so altogether it's 17. So now what happens if you are headed due north at 12 miles an hour, but you have a wind coming out of the west at 5 miles per hour? Where are you going to wind up?
Slightly off course.
Slightly off course? Exactly where?
To the east.
Yeah, but exactly where? Oh. And how far would you travel? Yeah, if
5 miles east.
5 miles east and
12 miles north.
12 miles north. If you add these two vectors, you put the tail of one at the head of the other, push them together, and now from here, which was your starting point, if you add the two vectors together, the resulting force pushes you to the right, or to the east, and that's where you wind up. How far would you have traveled? 13, right. How'd you do that?
Looked.
You just looked?
I mean, because that's
What do we call it?
so you use the Pythagorean theorem.
Pythagorean, yeah, it's a Pythagorean triple. So you would get pushed off to the right, to the east. This is where you'd wind up. This is the path you would take. And this is the vector that would represent what happened to you. You have traveled 13 miles. And there's your vector. Now the question is, exactly where 13 miles away? How are you going to find exactly where we wound up? Okay? You've probably heard in the movies, or maybe somewhere else, you've heard people describe something, a position in terms of a bearing of so many degrees and a distance of so many miles. Right? It actually means from north, clockwise, the measure of the angle. So in this case, there's your theta. That would be the bearing of where you would wind up. What is that angle? How would you find that angle?
Using sine, tangents, and cosine.
Right, exactly. So go ahead. Use your calculator. We've got the 5 is that length on the triangle. You've got 12 is that length on the triangle. You've got theta is that angle. Right? We've already figured out 13. But the tangent of theta degrees is going to be 5 over 12. And that's roughly 23 degrees. Different. What if instead of starting out by saying we were traveling north this much and traveling east that, or getting an east headwind that much, what if I just said, here's your vector. It's a bearing of 23 degrees and it's 13 miles. What we did the first time is actually work in terms of components, right? The two directions that created this, right? The two forces that created this, one vertical and one horizontal. No matter what vector I draw, it's going to have some component that is horizontal, right? That moves left and right, and some component that takes it up and down, north and south. Now, when we do this, we're going to identify separately the x direction and the y direction. So in terms of identifying vector c by its components, we'd say we went so many spaces this way, so many spaces that way, but since we're dealing with vectors, we have unit vectors. Right? Instead of saying, one space to the right, the unit vector left and right is I, and the unit vector north and south is J. Okay? Those are defined that way. Okay? Vector I is the unit vector horizontally. Vector J is the unit vector vertically. So what happens here? Well, we've got 5I, right? So vector C, if I want to write it in terms of its components, would be 5 times vector I plus 12 times vector J. Okay? And that's how you would write it in terms of its components. Now keep in mind, there's really not much different here. Okay? The real, it's essential here that you don't freak out. Because if you think about this, all I'm really doing is, same as we did last semester, we're starting off by defining some new terms for stuff we've already talked about. Think about it. In the past, it would not have been, in 6th grade or 7th grade, it would not have been unreasonable to give you the word problem. Somebody started at a certain point, traveled north 12 miles, then traveled east 5 miles. How far is he from where he started? Right? That's a word problem you have done before. Okay? That's really all we're talking about, except now we're talking about it in terms of vectors, because we're not just talking about the path, we're also talking about the forces that make it happen, the displacement. That's it. I mean, that's everything that you need to know for the moment about vectors. You know what the definitions are, you know what they add up, how to add them, how to subtract them, and again, what I want you to see, right, just like last semester, right, the objectives in the textbook are written clearly. For 6.6, it's just given two vectors, add them to find the resultant vector. Okay, that's what you need to do. Then, what do you have to know? You have to have the definition of a vector, vector addition, right, which is what we just did, and then finally, components of a vector. Right? What about this? Does this make sense? Why? I'm going to leave you to think about that, okay? And you should. You should think, why is that true? Based on everything we know about sine and cosine and the definitions, does it make sense that that's true?